Welcome to G Fun Facts Online. Today we are exploring a technological breakthrough that challenges everything we know about how we see the world. Imagine holding a camera that is the size of a coarse grain of salt. It has no glass lens. It has no focusing ring. It has no moving parts whatsoever. To the naked eye, this device looks like nothing more than a speck of dust sitting on a microchip. Yet, this tiny speck can capture full-color, crisp images that rival those of a conventional camera 500,000 times its volume. This is not science fiction. It is a reality developed by researchers at Princeton University and the University of Washington, and it represents the dawn of a new era in visual technology called lensless imaging. For centuries, the fundamental design of the camera has remained virtually unchanged. From the camera obscura of the Renaissance to the high-tech DSLR on a modern film set, the principle has always been the same. A glass or plastic lens bends light to focus an image onto a surface. Whether that surface is chemical film or a digital sensor, the optics, the glass itself, have always been the star of the show. But there is a problem. Lenses are heavy, they are expensive, they are fragile. And most importantly, they are constrained by the laws of physics. They require a certain focal length, which dictates the distance between the lens and the sensor. This is why your sleek, thin smartphone still has that annoying camera bump sticking out of the back. Lenses also struggle with aberrations, distortions, and depth of field issues. But what if we could throw the glass away? What if the intelligence of a camera didn't reside in curved pieces of polished glass, but in the mathematical algorithms processing the light? This brings us to the fascinating world of computational imaging. This is a field where hardware and software are no longer separate entities. They are co-designed to achieve the impossible. In this new paradigm, the camera is no longer just a box that records light. It is a computer that solves a puzzle. By replacing the lens with ultra-thin masks, diffractive gratings, or even a single pixel, and pairing them with powerful reconstruction algorithms, scientists are unlocking capabilities that traditional optics could never dream of. We are moving from the age of taking pictures to the age of computing images. To understand why this is so revolutionary, we need to look at the tyranny of the lens. A traditional camera is what we call an isomorphic system. It maps points in the physical world directly to points on a sensor. If you look at the raw data hitting a sensor in a standard camera, it looks like the image you see on the screen. The lens does the heavy lifting of organizing the chaotic photon streams of the universe into an orderly 2D projection. However, this convenience comes at a steep price. Aside from the form factor and the camera bump we mentioned, there is the issue of cost and complexity. High-quality lenses are triumphs of precision engineering. Correcting for things like chromatic aberration, where different colors focus at different points, requires multiple glass elements, complex coatings, and precise alignment. This drives up cost and weight. Furthermore, in fields like microscopy, you generally have to choose between seeing a wide area or seeing fine details. Lenses struggle to do both simultaneously without becoming massive and incredibly expensive. Computational imaging asks a radical question. Why does the raw data need to look like an image? In a lensless system, the raw data recorded by the sensor is unrecognizable to the human eye. It looks like static, noise, or a blurry wash of gray. It is a multiplexed signal, where light from every point in the scene is spread across many pixels on the sensor. To a human, it looks like garbage. To an algorithm, it is a treasure trove of encoded information. By shifting the burden of image formation from physical glass to digital computation, we gain immense flexibility. We can make cameras flat like a sheet of paper. We can refocus images after they are taken. We can capture 3D depth information from a single snapshot. We can even see light that is invisible to the human eye, such as infrared or terahertz radiation, using sensors that don't require expensive exotic glass lenses. So, how do you form an image without a lens? If you simply remove the lens from a camera, light from every point in the scene hits every pixel on the sensor. The result is a featureless gray blur. To create an image, you need to modulate the light. You need to block, bend, or scramble it in a known, predictable way, so that you can untangle the mess later. The simplest form of lensless imaging is the pinhole camera. By restricting light to a tiny hole, you ensure that light from a specific point in the scene can only hit a specific point on the back wall of the camera. It effectively filters out the chaos. However, the pinhole is a poor solution for modern imaging because it suffers from a brutal trade-off. If the hole is too large, the image is blurry. If the hole is too small, diffraction blurs the image, and almost no light gets through, requiring exposure times of seconds or minutes. Modern lensless cameras solve the light throughput problem of the pinhole by using coded apertures. Instead of one pinhole, imagine a grid with thousands of pinholes arranged in a specific pattern. This allows 50% of the light to pass through, solving the brightness issue. However, now you have thousands of overlapping images on the sensor. This is where the math begins. In optical engineering, the behavior of a system is described by its point spread function, or PSF. This describes what a single point of light in the world looks like when it hits the sensor. In an ideally focused lens, the PSF is a single, sharp dot. In a lensless system, the PSF is a complex, large pattern. It might be a shadow of the coated mask, a caustic light splash, or a diffraction pattern. Because light behaves linearly, the image on the sensor is simply the sum of all the PSFs from every point in the scene. If you know the pattern, the PSF, and you have the recorded mess on the sensor, you can mathematically reverse the process to find the original scene. This is a classic inverse problem. While early lensless experiments used amplitude masks, which are essentially opaque sheets with holes, modern systems often use phase masks. Amplitude masks block light, which is inefficient because you are throwing away photons. Phase masks are transparent materials, like glass or plastic, with varying thickness. They don't block light, they delay it. As light waves pass through thicker and thinner parts of the mask, they interfere with each other, creating a complex diffraction pattern on the sensor. This is the secret behind the grain of salt camera we discussed at the start. It uses a metasurface. This is a surface studded with millions of microscopic pillars. These pillars act like antennas for light, slowing down wavefronts by precise amounts to shape the light field. Unlike a lens that forces all light to converge, this metasurface encodes the light in a way that an AI algorithm can decipher with extreme precision. Now let's look at the different technologies driving this revolution, because there is no single lensless camera. One of the pioneers was the flat cam, developed by researchers at Rice University. It placed a coated mask just millimeters above a standard camera sensor. It works like a collection of thousands of pinhole cameras. The advantage is that it is thinner than a coin and can be manufactured using standard lithography techniques, just like computer chips. However, because it blocks light, it struggles in darker environments. To solve the light loss problem, researchers developed technologies like flat cam and diffuser cam. Diffuser cam, developed at UC Berkeley, uses something incredibly simple. A piece of bumpy plastic, essentially a diffuser, similar to the privacy tape you might put on a bathroom window. When placed in front of a sensor, it creates caustics. These are sharp, focused lines of light intensity, like the patterns sunlight makes on the bottom of a swimming pool. The magic is that these caustics preserve high-frequency information, or sharp edges. This allows the system to reconstruct 3D images from a single 2D snapshot. Because the pattern of the caustics changes predictably depending on how far away an object is, the algorithm can calculate depth purely from the blur. Perhaps the most counterintuitive device in this field is the single-pixel camera. A standard camera has millions of pixels and one lens. A single-pixel camera has millions of lenses, or mirrors, and one pixel. It uses a digital micro-mirror device, or DMD. This is a chip with millions of tiny mirrors that can flip on or off thousands of times per second. The DMD reflects light from the scene onto a single photodetector. The camera projects a series of random patterns onto the scene, or modulates the incoming light with these patterns, and the single pixel records the total intensity for each pattern. Using a mathematical theory called compressive sensing, researchers can reconstruct a full megapixel image from far fewer than a megapixel's worth of measurements. Why would you use this? Well, single-pixel detectors can be made very exotic. It is expensive to build a megapixel sensor for infrared or terahertz wavelengths. It is cheap to buy one high-quality sensor. This architecture is revolutionary for seeing through smoke, fog, or in non-visible spectrums. Taking the concept of computation to the physical limit, researchers at UCLA created diffractive deep neural networks. Here, the physical mask is the computer. They 3D print layers of transmissive material. The thickness of each point on the layer is calculated by deep learning to act like a neuron in a network. As light passes through these layers, the diffraction performs the calculation. By the time the light hits the detector, the processing is done. This allows for object recognition or image classification at the speed of light, with zero power consumption for the computation itself. Of course, a lensless camera is only as good as its reconstruction algorithm. This is where the computational aspect truly shines. Mathematically, the imaging process involves inverting a massive, complex matrix. Early reconstruction used classical optimization methods. These were mathematically robust but slow, often taking seconds or minutes to reconstruct a single image. The game changer was the introduction of deep learning. Instead of mathematically modeling the diffraction perfectly, researchers trained convolutional neural networks, or CNNs. They show the AI pairs of scrambled sensor data and ground truth images. The AI learns to reverse the distortion. Recent advances use generative adversarial networks, or GANs, and diffusion models. The AI effectively hallucinates the fine details based on its knowledge of what the world generally looks like, filling in the gaps that the lensless sensor missed. This leads to photorealistic results. The cutting edge, such as Deep LIR, combines the physical model of diffraction with AI to ensure data consistency while cleaning up noise. Why go through all this trouble? Because lensless imaging unlocks applications that are physically impossible for glass lenses. In medicine, size matters. To look inside narrow blood vessels or delicate neural pathways, you need the smallest possible camera. Fiber optic bundles are expensive and pixelated. Chip-on-tip endoscopes are limited by the size of the lens stack. A lensless sensor can be the thickness of a piece of tape. Researchers are developing bio-flatscope devices that can be implanted into the brain to monitor neural activity in free-moving animals. In the future, you could swallow a pill camera that is essentially a speck, capturing 3D views of the digestive tract without the bulk. Then there is the Internet of Things and the concept of smart dust. Putting a camera on everything raises cost and privacy concerns. But a lensless camera in a smart home sensor captures a blur. If a hacker intercepts the data stream, they see noise. The reconstruction key can be kept secure. Furthermore, the system can be designed to only detect occupancy or falls without ever resolving a face. Because lensless cameras can be printed like semiconductors, they can be embedded into walls, clothing, or even wallpaper. In the automotive world, autonomous vehicles need to see everything, but they are currently covered in bulky sensor pods. Since lensless cameras are flat, they could be laminated directly into the glass of a windshield, turning the entire surface of the car into a sensor array. Companies like Metalens are using metasurfaces to steer light for 3D sensing without moving parts, making robust depth sensors for cars. Researchers at the University of Utah even demonstrated a camera made from a window pane. By wrapping reflective tape around the edge of a glass window and placing a sensor on the side, they used the internal reflections of the glass itself as the lens to reconstruct an image of what was outside. This suggests a future where every window in a building could essentially be a camera, invisible to the occupants. Despite these breakthroughs, we won't be throwing away our professional glass lenses tomorrow. There are challenges. While phase masks improve upon pinholes, lensless systems still struggle with contrast. In a traditional camera, a black pixel on the sensor means no light hit it. In a multiplexed lensless system, light from the whole scene hits every pixel. This background glow or shot noise can drown out subtle details, especially in low light. There is also the computational load. A glass lens processes light instantly, for free. A lensless camera requires heavy computation to generate a viewable image. For real-time video, this requires significant processing power, which drains battery. Finally, there is the hallucination problem. As we rely more on AI to reconstruct images, we face the risk of generative artifacts. If a lensless security camera sees a blurry blob and the AI reconstructs a face, is it the real face or the face the AI expects to see? Ensuring the scientific fidelity of reconstructed images is a major hurdle for medical and legal applications. We are standing at the precipice of a transformation as significant as the shift from film to digital. That shift changed how we stored images. This shift changes what an image is. In the lensless future, a camera is not a mechanical eye. It is an information sponge. It is a piece of smart glass, a sticker on a wall, or a microscopic implant. It is a device that trades the bulk of physical glass for the elegance of mathematics. The grain-of-salt camera is just the beginning. As metasurfaces move from university labs to semiconductor foundries, and as reconstruction algorithms become faster and smarter, the definition of photography will expand. We will take pictures without cameras. We will see the invisible. And we will realize that the best lens was never a piece of glass at all. It was the code we wrote along the way. Thank you for listening to G Fun Facts Online.